Hi guys, this is the first video in a series of videos which will cover NMR. In the videos I will go through the handout, the NMR handout, and you should have this handout with you as you watch the videos. The first page of the handout is a set of warm-up questions which will give you an idea of some of the types of questions we will be working towards answering. Most of these questions are fairly straightforward once we learn a little bit of NMR. One sort of introductory concept which we will have to become familiar with is predicting how many signals are expected in the NMR of such a compound. Now when we say NMR, this includes both proton NMR, or so-called 1H NMR, or hydrogen NMR, but we will also be looking at carbon-13 NMR. These are the two most common NMR types. Okay, so that's a warm-up page. Now this page here obviously shows two IRs. But let me ask you, which compound, we have two alcohols here, a primary alcohol and a secondary alcohol, which alcohol goes with which IR? Now both IRs show OH peaks. Both IRs show sp3CH, and both IRs show a fingerprint region. Now obviously the fingerprint region is different, but with any fingerprint we're going to have to match that up. We have to have a standard to match that with. We can't just look at a fingerprint and tell which compound it is. In the end, it's very difficult to tell which alcohol goes with which IR. And this is a limitation of IR. On the other hand, if we look at the proton NMRs, or hydrogen NMR of each compound, as shown on this next page, it's very easy to tell which compound goes with which NMR. Now, at this point, you're not going to be able to determine that. But once we look at a little bit of NMR, this will become quite apparent. I've actually gone ahead and assigned these here. The top spectrum is the primary alcohol, and the bottom spectrum is the secondary alcohol, or isopropanol. Now, key thing with proton NMR, which looks at the protons in the compound, is we need to be able to tell how many different types of protons are in a given compound. Now, one propanol here has actually four different types of protons. And I've labeled these as A, B, C, and D. The three H's on this carbon are all the AH's, the two H's there are B, the two H's here are C, and the H here would be a fourth one, D. And it turns out in NMR that each type of atom is going to give a signal. And so we have four different types of protons, and actually in the NMR we have four signals, 1, 2, 3, and 4. On the other hand, if we look at isopropanol, because of symmetry, the two CH3s are equivalent. They're identical. And so that's only one type of hydrogen, labeled as A. Then we have the CH, that's B, and the OH, that's C. And so we have only 3 types. And so we expect only 3 signals in the HNMR, and indeed we have 3 signals. So number of signals is one of the first things we need to be able to address. Now, we also have splitting of the signals. Common terminology is triplet, that's a T for me, triplet 2H, singlet, multiplet, triplet. Now this at the beginning here is sort of an overview, introduction. We will go into each of these specific topics in detail as we move through the handout. Below we have a multiplet, which is for 1H, a singlet, and then a doublet. That is, what we have here is this signal is 2 lines. It's 1 signal, 2 lines, we call it a doublet. This signal is 1 line, it's called a singlet. This signal is multiple lines, and usually when it's more than 4, we start calling it a multiplet. So that's a multiplet. Now what we'll also see for proton NMR is the integration of the signal, that is the area under the curve, correlates with the number of protons. Now the integration is not shown on these spectra here. These may be computer-generated spectra. We'll learn about integration and how to determine integration, but this integrates for 1H, and that integrates for 6H. The integration, in this case, can tell you that this must be for the A hydrogens, because there's 6 A hydrogens. B, there's 1. That's the signal here. We'll also learn that we expect B to be a multiplet. Indeed it is. We will also learn that A should be a doublet. Indeed it is. We will also learn that A should be more upfield compared to B. Or on the other hand, we can say that B should be more downfield than A, and indeed it is. C is the OH, it's 1 hydrogen, it's integrating for 1 hydrogen. Now OHs can be variable in their placement on the NMR spectrum. Okay. Now see, lots of detail here that comes from your peaks, lots of information about the peaks, integration, splitting, peak position, where with IR, mainly we looked at peak position. We never looked at like how many peaks were here at the sp3ch region. Because of the much more detailed information given by an NMR, NMR is typically much more powerful and informative than IR. Now as we move along, you'll probably want to refer back to these sort of introductory spectra to review what we've been talking about. Here I just give you another NMR as an introductory example. This is a proton NMR of melatonin. Multiple signals. I also give you the IR of melatonin. One thing that we'll be working towards is being able to work comprehensive spec problems. These can be found in your workbook, such as on page 15. And these are the types of problems that will appear on each test in Organic 2. They will include IR, mass spec, proton NMR, as well as carbon NMR. Now proton NMR is going to show all your protons, while carbon NMR, you guessed it, will show all of your carbons. And since most organic compounds contain a good number of carbons and hydrogens, that's the main reason why these are the two most important types of NMR. And the goal for such a problem is to come up with the structure of the compound based on all the spectra. There may be some chemical information given, like chemical test information. Okay. All right. These first couple of pages we're doing some sort of overview of NMR, an introduction. Let's get a little bit more into the details here. This page called Spectrum Overview. This is a typical proton NMR. The x-axis here is your parts per million. Okay, ppm. We'll talk more about that as we go along. Typically, proton is about 0 to 10 or 0 to 12 ppm. Now, when we get to carbon NMR, it'll be like about 0 to 200 ppm. So it's very easy to tell we're looking at a proton NMR here because we have the 0 to 10 to 12 ppm range. Okay, this compound here is benzylamine. Number of signals, we expect the NH2 would be one signal, the CH2 would be another signal. We would actually expect 3 different signals for the hydrogens here, like these two are the same, these two are different, and then that would be a third. In this particular spectrum, all of these aromatic hydrogens are given a peak very close to each other, and they're actually on top of each other, and it looks like it's basically one signal. Theoretically, we expect 3, it's only 1. We'll talk about such. Both of these are singlets. You would expect singlets for both of these. The CH2 is probably this peak here, while the NH2 is most likely this signal. Now, with any NMR you run, you need to include an internal standard. The internal standard sets the baseline. And we typically set the internal standard at 0 ppm here. The most common internal standard is TMS. Shown here, it's a silane. Silicon is just below carbon in the periodic table. It makes 4 bonds like carbon. Silicon bonded to 4 methyls. It's called tetramethylsilane, TMS. It's used for both proton and carbon NMR. It gives just one signal because all of the H's here, all 12 H's are the same. One signal, and that signal is a singlet. We set that singlet at 0 ppm. We'll talk more about why an internal standard is needed. It's not needed with IR, but it is needed with NMR. Okay, some terminology. Well, as written here, signals that are more to the left in the spectrum, that is a higher ppm, these signals are said to be downfield. Signals that are more of a lower ppm, or to the right in a typical spectrum, that's said to be upfield. Now, students sometimes get this sort of backwards because higher number sounds like it may be going up. Sometimes students call this upfield, going this way. It's actually wrong. It's downfield, that's upfield. We may point out where this terminology came from in just a minute. Okay, let's go through this box here, which gives some relative terms. All right, protons that give signals more downfield. Okay, this is this end versus this end. These protons are said to be more in electron-poor environments, where protons in more electron-dense or electron-high environments are going to give signals more upfield or to the right. Protons that give signals to the left or more downfield are said to be deshielded, where protons which give signals more upfield are said to be shielded. We've already covered the downfield versus upfield. Frequency. Now note, we're plotting ppm. We do not plot frequency and we do not plot wavelength in NMR. If you remember, what do we plot in IR? In IR, we plot wave number, which is reciprocal centimeters. And the centimeter is a indication of wavelength. So it's essentially wavelength, but we do a reciprocal, and thus we call it a wave number. If you remember, what did we plot in UV vis? In UV vis, we plot wavelength directly. But there, the wavelength is much shorter because UV and visible are higher in energy than IR. Instead of being on centimeter scale, it's on nanometer scale. Okay. Well, NMR is also a spectroscopy. We do use light, electromagnetic radiation. But what we use is radio frequency. We'll talk more about that. But we don't plot frequency and we don't plot wavelength. Instead, we plot ppm. If we were to plot frequency, the left side would be your higher frequency side, and your right side would be your lower frequency side. Now, of course, frequency correlates with energy, so the left side would be high energy, and the right side would be lower energy. Ultimately, the signals that are on the left side that are more downfield required more energy for the absorption to take place, a higher energy of electromagnetic radiation. Okay, finally we have delta values. Delta value is essentially equals ppm. These are delta values. A lot of times we just say 4 ppm or 8 ppm, but the 8 is a delta value, so higher ppm equals higher delta value. Typically I'll just say, what's the peak position? And the response can be, 3.8 ppm. And we may not ever use the term, what's the delta value? Okay, terminology is very important if we're going to be able to discuss NMR. Let me try to explain the upfield downfield. This came about because in the olden days you used to vary the magnet, and we haven't even talked about the magnet that's being used yet. But to get these signals to appear, you had to turn the magnet up. And to get these signals to appear, you had to turn the magnet down relative to that. So for example, if this peak was absorbing, and then you wanted to see this peak, you would have to turn the magnet down to then see this peak. And so that's why this became known as downfield. Now that may not mean much to you right now, but eventually that may make more sense. Okay, sample prep. How do you run an NMR? Well, first off, you have to have a magnet. You have to have an instrument. But how do you prepare your sample? Typically, NMRs run in solution. Okay, when we do IR these days, we can do it neat. That is, just take the pure compound and position it on the IR, and we can run the spectrum. Typically today we still do NMR in solution. We have to dissolve the compound. We take a few milligrams or more. Carbon NMR requires more compound. So about 5 for proton, anywhere from 20 to maybe 50 milligrams for carbon NMR. Dissolved in a suitable solvent. Importantly, though, that you do not want your solvent to give many NMR peaks. Because when you look at your spectrum, you don't want to have peaks for your solvent. That'll just complicate your spectrum. Now, most solvents are going to contain protons. One that does not, and it's sometimes used for NMR, is carbon tetrachloride. Carbon tetrachloride, commonly called carbon tet. The problem with carbon tet is, well, it has a number of problems. It's nonpolar, and so it doesn't dissolve a large number of compounds. And if your compound has any degree of polarity to it, it may not dissolve in carbon tet. Carbon tet is also fairly toxic, and it's an ozone depleter. Now, chloroform, if we replace one of the chlorines with a hydrogen, chloroform, now polar, it's a much better solvent. It will dissolve many more types of compounds. The problem is it now has a hydrogen, and that hydrogen will appear in your NMR. Now that may be okay, but the major problem is your solvent is going to be there'll be much more solvent than your solute. And so the signal for this H will be much more intense than the signals for your compound, and it will end up swamping out the signals for your compound. Well, so where does that leave us? Well, there's a variety of tricks you may do here, but one sort of ingenious trick is that chemists have done is replace this H with a deuterium, which is just an isotope of hydrogen. The solvent still has pretty similar properties as the proton version. But now with deuterium, no signal will appear in your proton NMR spectrum. And this is very commonly done. And we call this sort of like chloroform D. Okay. Another common solvent is DMSO. This would be CH3SOCH3. It's more polar than chloroform. If your compound is highly polar, it may not even dissolve in chloroform. DMSO would be a better choice. Many hydrogens here. Instead, we replace these with D, and so that would be D3, D3, and this would become DMSO D6. with the D usually written in lowercase. Not sure why that convention is. Lots of deuteriums there in that compound. But DMSO can be made, it can be bought. It's a little expensive. But these are the two most common deuterated solvents used for NMR. Now, when you prepare your sample, it's done in, I have a tube here. You make your solution in like a vial, and then you pipette it into what's called an NMR tube, just a slender tube about the size of a straw. Then you put a little plastic cap there, and you have your solution, and this is going to go in the magnet. Now, you want to include your standard TMS. In the olden days, you would then take this and add in like a drop of TMS to this solution and mix it in. Today, though, most of the time you buy your NMR solvents, they already include TMS. And so this will include like 0.1% TMS there, and you just buy that. And that's what I have here. Okay. All right, let's get into it even further. What is NMR? First off, what does NMR stand for? NMR stands for nuclear magnetic resonance. Why these three terms? Well, it's because NMR deals with the nucleus of the atom. Okay? IR dealt with the bonds and the vibration of the bonds. NMR deals with the nucleus. Now, this can be the nucleus of the protons, if you're doing proton NMR, or if you're doing carbon NMR, it would thus be the nucleus of the carbons. Okay? We're looking at the magnetic properties of the atom. More specifically, we're looking at the magnetic properties of the nucleus. So that's where the magnetic comes from. Resonance. Resonance is sort of an old term for when absorption of the radio frequency takes place. An absorption. We say it's resonating. And so basically it's sort of a nuclear phenomenon. It involves some magnetic properties and we get an absorption or resonance. And that's where the term NMR comes from. Okay. The NMR phenomenon, which I title this section, that is, how do we get a signal? What's going on with NMR? We'll see that sort of down here. But first, let's make a few statements. It turns out that all nuclei, okay, again, we're dealing with the nucleus. Any nucleus with a net spin, any of these will have a magnetic moment associated with them. All right? Spin was a spin quantum number, I. A nucleus that has a net spin is going to have I greater than 0. Okay? If I equals 0, that means there's no net spin. But if it does have a net spin, it will have a magnetic moment associated with it. Why is that? Well, it's just physics. As you learn in physics, a spinning charge produces a magnetic field. So if the nucleus, by the way, what's the charge of a nucleus? Positive, because that's where the protons resolve. And neutrons, but they're neutral, it's net positive. But if that net positive nucleus is spinning, it's going to create a magnetic field. All right? So before we move on, how do you tell if a nucleus is going to have a spin quantum number of greater than 0? Well, this is how. Any nucleus with an odd number of protons or neutrons will have a spin quantum number of greater than 0. All right? Now, to be NMR active, it has to have a net spin and thus a magnetic field. Based on this, it turns out that any nucleus with an odd atomic number or mass will have a magnetic field, and thus it will be NMR active. Odd atomic number or odd mass number. So, let's take some time to look at some examples here. Hydrogen 1. All right. Now the lowercase 1 would be the atomic number. It's redundant. If there's an H, we know that's 1. The mass number being 1. All right. 1H said. How many protons? Well, 1. Atomic number of 1. How many neutrons? 0. All right. But it's got 1 proton, which is an odd number. So the spin quantum number should be greater than 0. Thus it should have a magnetic moment associated with it. Thus it should be NMR active. Yes. What about deuterium, which is isotope of hydrogen, in which it has 1 proton and 1 neutron, and those add up to be 2, so the mass number is 2. We call that deuterium. Is that NMR active? Yes. It has both 1 proton and 1 neutron. Both of those are odd. Remember, it only takes one of these being odd to be NMR active. Deuterium, NMR active. What about carbon? Okay, the most common isotope of carbon is carbon-12. That would be 6 protons and 6 neutrons. Is this NMR active? No. Neither proton nor neutron is odd. The spin quantum number of carbon-12 is 0. It has no net spin. It does not have a magnetic moment associated with it. Thus, turns out you cannot do NMR on carbon-12. Okay? Not NMR active. But what about carbon-13? 6 protons, 7 neutrons. Neutrons odd? Check. It will have a magnetic moment associated with the nucleus. It will be NMR active. Thus, whenever we do carbon NMR, we're only doing NMR on carbon-13. Now, of course, carbon-12, if you remember, equals about 99% of your carbons. Carbon-13 equals about 1%. This is an organic compound in this NMR tube here. If I ran a carbon NMR on this compound, only 1% of the carbons are going to be NMR active. That is, only 1% of the carbons are going to give signals. That's okay. We can still get information from those 1%. One of the practical issues, though, is we typically have to use more compound if we're going to do a carbon NMR. I mentioned that over here. Okay, about 5 milligram for proton, and about, it can vary, about 25 milligram for carbon-13, plus more scans. More compound, also longer scan time for the carbon. largely because, or predominantly, or this is why. Right there. Okay. Now, most all, 99% of your H's are 1H. So essentially all the H's of a compound are NMR active. Okay, what other atom types can we do NMR on? Well, it turns out you can do NMR on just about any element on the periodic table, as long as you got the right isotope. Okay? Isotope must be NMR active, and we talked about how you determine that. Fluorine is commonly done. All right? Now, the most common isotope for fluorine is fluorine-19. Of course, that's 9 protons and 10 neutrons. NMR active because the number of protons is odd. You can do NMR on any isotope of fluorine, because any isotope of fluorine is going to have an odd number of protons. Fluorine-19, oxygen. Now, the most common isotope of oxygen is 16, but that's 8 protons and 8 neutrons, not NMR active. However, O17 is, and that's 8 protons and 9 neutrons. Check. At least one of those is odd, NMR active. O17, while it's a very minor isotope of hydrogen, it's still significant enough that we can do oxygen NMR probing the O17 nucleus. Let's try another one. What about what about 10-119? Is that isotope of 10 NMR active? Yes. Well, you can tell that because the mass number is odd. That means one of the either proton or neutron must have been odd for that to be odd. Well, we can just look at the periodic table. For 10, atomic number is 50. That means it's got 50 protons and 69 neutrons, NMR active. Okay? One of those is odd. On the other hand, 10-118 would be 50 protons and 68 neutrons, and that isotope would not be NMR active. Now, I've never seen any 10 NMR done, but theoretically it can be done. But if you looked online, you may come across somebody out there doing NMR on 10, but they're likely doing it on 10-119 or maybe 10-117. I'm not sure which isotope is most common, but they're certainly not doing it on 10-118. Okay. Now let's look at the absorption process. So, let's assume we're working with a nucleus or nuclei which have a magnetic moment. Now, with a given sample, we have billions and billions and gazillions of nuclei in the tube. Let's say we just want to probe the proton NMR, protons. Okay. So let's just focus on the protons. There's still a gazillion protons there. They all have a magnetic moment. It turns out that just in a everyday state, like in the tube right here, The magnetic field directions of these protons are all random directions, okay? They're not oriented in any direction. The orientation is all random. But if you place this compound, these nuclei, in an external magnet, something very interesting will happen. It turns out that the nuclei, the field directions, the direction of the magnetic moments, they will line up in two different ways. They will line up either with the external field in the same direction as the external field, and that's called the alpha state. But some of them will also line up exactly opposite the external magnetic field, and that's called the beta state. Now the alpha state is lower in energy because it's aligned with the larger field. The beta state is higher in energy. A consequence of this is we now have two discrete energy levels with a delta E, a difference of energy between them. Okay? This only occurs when the sample is in the presence of an external magnetic field, a large magnetic field. Okay, the magnet. If we're not in a magnetic field, all of the field directions are random, and we do not have two discrete energy states. One question sometimes students ask is, why would some line up opposing the field? Well, sometimes you hear the analogy of like a canoe in a river that's moving sort of quickly. You can line that canoe up sort of straight downstream, but you can also line that canoe up sort of facing upstream. And you can hold it there upstream. And it's almost just as easy to hold it facing upstream as it is to hold it facing downstream. What's more difficult is to try to hold your canoe sort of perpendicular to the stream. That's going to be more difficult, like this, because this type of positioning would experience a torque, and it would be turned either, it would be turned to become parallel to the field. So this is actually what's higher in energy. These two are actually almost equal in population. There's a slightly few more in the alpha state than the beta state. Okay, but the main thing here is because of the external magnetic field, we now have two different states. Our nuclei are now in two different states, and this is going to allow us to do a transition and to have an energy absorption. Okay? And this little small diagram shows that, where if you're in the alpha state, we can absorb light energy, and we can do a sort of what's called a spin flip. The orientation is flipping from being inline to opposing. It's just basically called a spin flip. And the system can absorb light energy, and we can plot that absorption. Now, it actually turns out that in the modern instruments, what we usually plot is sort of the reverse of that. Nuclei in the higher energy beta state can also relaxation. They can relax back down to the alpha state. And when they do this, they give off energy. And you could also measure how much energy is given off. Okay? But this absorption either way you want to call it, the measurement of the absorption or the measurement of the relaxation, this leads to an NMR spectrum. All right. But we have a ways to go, though. We have a ways to go. This next page will sort of get us there of how we can ultimately turn this information into sort of different signals on our NMR spectrum. Before we get down here, though, let's look at this diagram. I introduced B naught. Go back over here. The external magnetic field has a strength. That strength is usually referred to as B naught or H naught. B or H is the same thing. Unfortunately, two different sort of descriptors have come into existence. But that's the external strength of the external magnet. Importantly, the delta E is proportional to the strength of the external magnet. Okay, what is the delta E? The delta E is the gap between the alpha state and the beta state. It's the difference in energy between the two states. All right. The delta E is proportional to the strength of the external magnet. And we can actually plot that correlation. And that's what this figure 1 here shows. B naught, okay, that's the external magnet strength again. This showing the alpha state and the beta state. And as the external magnetic field strength increases, the gap is going to increase. Okay? This can go on and on and on. But if the field strength is here, we're going to have, this gap. But if the field strength is here, larger, then we'll have a larger gap. So it's really a simplistic diagram, just make sure you understand it. Now importantly, what if the field strength was 0? That is here. That is, if it's 0, that means we do not have a magnet. Well, if you have no magnet, there is no difference between the two states. Okay? All states have equal energies. And if there is no magnet, you're basically going back to this here, where there is no difference in energy between the two possible states. There are no two possible states. Only with a magnet do we have two possible states, and the stronger the magnet, the greater the gap, or the greater the difference between the two possible states. Okay. Now, how do we get different signals in an NMR? I mean, back over here we had 4 different signals. How do we get different signals? Well, various NMR signals come from various delta E's for different protons. Okay? So if we go back over here, we have 4 different types of protons here. Each H type has a different delta E. And that's why we're getting different absorptions. We have different delta E's. Remember, the absorption takes place when alpha is flipped to beta. Okay? This is your different delta E. That means if delta E varies, it's going to take variable energies for the transitions to take place, and thus the variable energies are going to give you variable absorption peaks in your NMR spectrum. Okay. But here's a dilemma at this point, something that doesn't quite make sense. All protons are in the same magnet, okay? We take this and we put it in the same magnet. So shouldn't all protons be experiencing the same magnetic strength? Well, the answer is yes and no. They do experience the same magnetic strength from the external magnet. Okay? But each proton also experiences a local magnetic field. A local magnetic field due to the electrons that are nearby the protons. Okay, the proton is bonded to maybe a carbon. There are electrons in that bond. Those electrons create a local magnetic field which we have to add to the external field. Well, actually we subtract it because of Lenz's law. The local magnetic field, by the way, this is generated because of the magnet. But since this is an induced magnetic field, it's going to oppose the external field. That's Lenz's law. You may see this in physics. So I call this B electrons. The electron field of the magnetic field of the electrons is going to oppose the external magnetic field. All right? And so we can get to this sort of summary equation where B effective, all right, this is the B that the H feels. This comes from the external magnetic field, which is constant for all protons, minus the local magnetic field due to the nearby electrons, nearby the hydrogens. But importantly, okay, this varies. Okay, this essentially varies due to variance in electron density nearby the H. Now, let's bring in the term shielding, deshielding. Now, since the local magnetic field opposes the external, that's why we have a negative sign here. This is a shielding effect. Okay? Shield. Why do we call it shielding? Because it shields the protons from feeling so much external field. All right? Let's say the external field is, okay, we could talk about what type of units or Gauss the field strength is. I'm not going to take us there. Let's just say it's 10. Okay. Field strength of 10, but the local is 2. All right. That means the proton is only feeling 8. So instead of feeling 10, it only feels 8. So the electrons are shielding the protons from feeling the full extent of the external field. Ultimately, we say that the electrons act to shield the nuclei from the external field. Now, it turns out that higher electron density equals more shielding. Because higher electron density would be like 10 minus 3, and that would give you 7. This would be illustrating higher electron density. That would lead to more shielding, and so the nuclei only feel 7. It's more shielded, and we can do even more and more shielding. Actually, while we're talking about this, no, let's don't do that. I don't think that's going to be applicable. I was going to try to bring in the term deshielding. Let's just work with shielding right there. Let's see what this final graph will tell us here. Okay, this looks like our figure 1 up top. We could have two different delta E's. Smaller delta E is basically what I tried to show up here. Smaller delta E okay. How do we get two signals here? Well, we got two delta E's. Okay. That's basically two precise energies that are going to lead to spin flips. Okay. One spin flip is going to be easier. The delta E is smaller. It's going to be easier to do that flip. Lower energy here. Where this spin flip requires more energy because the delta E is larger, it's going to require higher energy. It's going to give you two different energy absorptions that we can plot. Let's look at this. This downfield. And upfield, comparatively. Remember, we said upfield came from shielding. Downfield came from deshielding. Remember the terminology? Remember we said this was higher frequency and higher energy, where this was lower frequency slash lower energy. Remember, this is all relative. This is shielding compared to this. So, would these two give these two signals? Well, this should be higher in energy, right? Greater delta E, higher in energy, and so it should be more to the left. Higher energy, higher frequency, more downfield. Shielding. Which one of these situations would arise because of more shielding? Well, shielding is going to lower the be effective. And to be effective is lower. Okay, this is essentially be effective. Up here we called it be not, but we hadn't brought in the idea of the be local yet. If the be effective is lower, it's going to give a smaller delta E. So it makes sense that this comes from shielding. And shielding is going to lead to lower energy needed for the transition. And that's why the signal is more towards the lower energy side. It's more upfield because it's shielded. Now this peak ultimately may come from shielding, because we don't know what B is. I mean, maybe B regular is here. And both of these come from shielding. But shielding, deshielding are usually used relative to each other. And that is, this peak is more deshielded compared to that peak. Okay, I could go on and on about this. Ultimately, what have we done here in the past 2 pages? We've done a spectrum overview with important terminology that will be used continuously. We talked about sample prep, pretty straightforward. The idea of deuterated solvents, deuterated chloroform, and deuterated DMSO being 2 most common. Then we talked about the NMR phenomenon. We talked about how to determine if a nucleus is going to be NMR active. Then we talked about the requirement of an external magnetic field. Basically, we need a magnet. That gives us 2 states. Now we can do an energy transition. All right. We can plot the absorption, or we can plot relaxation, and we'll use this term a little bit later when we get to carbon NMR. By the way, the amount of energy that it takes to do this turns out that it falls in the radio frequency. Ultraviolet will not do this. Visible IR will not do this. It's actually a very weak transition. Delta E is very small. We're using very low energy radio frequency. All right. We do NMR with radio waves. We talked about how the energy gap is proportional to the magnet. But then we said, well, if all the protons are in the same magnet, shouldn't there be the same delta E for all protons? And it turns out the answer is no, because different protons have different electron densities nearby. And the electrons serve to shield the protons from the external magnet. And the more electron density you have, the more shielding you're going to have. The local electron magnetic field opposes the external field due to Lenz's law. Well, that's a consequence of Lenz's law, which you will see in your physics book. I didn't mention this going through. External field. The electrons, it's sort of showing circulation of electrons. That's very general. Ultimately, the magnetic field for the electrons is going to oppose the external field. That's what we said here. Okay. The electrons act like sunscreen. The more electrons you have, the less the nucleus is going to feel the magnet or the sun. Two people can sit under the same sun, but one will get sunburned because the other had sunscreen on. The electrons act as sunscreen. They shield the nuclei from the external magnetic field, changing the B effective. But since different types of protons have different electron densities nearby, we get different signals for different protons. And we tried down here to turn a delta E, different delta E's into different signals, sort of using our knowledge of various things such as energies, shielding, deshielding, whatnot. Okay. I think I will end video 1 there. We've introduced largely the theory behind NMR. From here out, we're going to move towards more of the practical aspects of interpretation and using the NMR. But the foundation of the theory is very important, especially the terminology and understanding, how do we get a signal and it's not just magic. So it is useful to spend some time to understand the theory. But as we move forward, we'll be looking at more exact practical concepts, and these will include looking at number of signals. We'll do some practice there. We'll look at peak positioning. Where do we expect different peaks? We did a lot of that with IR. We'll look at integration of our signals. We'll look at the splitting of the signals. And then number 5, the sort of miscellaneous concept is the D2O shake. Okay? Okay guys, that ends video 1 of the NMR series.